My research is grounded in fluvial geomorphology. That means the shape of the river, how windy it is, how steep it is, how wide it is. I'm linking certain processes to this research, such as river ice behavior, how it freezes up, how it breaks up and jams. This determines the shape of the river that impacts the habitat for fish or bugs. And a lot of water quality processes are also dependent on the geomorphology of the river. We're looking how Lake Diefenbaker hydro generating power station, Cotto Creek, impacts the behavior of the ice cover. And we've been modeling those processes and determining how the variation in discharge from the plant can impact the river ice cover. This is a river ice model, and what I'd like to do with this model simulation is determine the formation of different ice types, but also ice thicknesses. Frazzle ice moves down the river here and gets lodged, and then it accumulates, and it's called juxtaposition of the ice cover. The ice cover moves upstream. This is indicative of certain ice thicknesses, but also ice type, where here we have maybe in the middle channel more of the rougher ice, and here along the sides here more the thermal ice, or the shore or border ice, we call that as well. We also need data here to calibrate and validate the model. Here's an example of a satellite image. The stretch that we modeled in the river ice model is this stretch right here. And you can see quite nicely the white ice part here. This is the main flow of the frazzle ice at the beginning of the freeze-up season. And the black ice, it's also a bit of a yellow tinge here. You can see at the shores and borders that it had formed there along the river. We also need data to ground truth the satellite imagery, and for that we use time-lapse cameras. This is an example of some time-lapse imagery at freeze-up. Here we have some slush ice moving down, and that slush ice accumulates to form flows, or what we call pancake ice, and that'll flow downstream until it finds a lodgement, and then it'll accumulate, and that ice cover will progress upstream. We also will go out in the field and take ice thickness measurements and make observations of ice type. The ice core is an important machine in our toolbox. It allows us to extract a core and help us to visualize what the profile of the ice layer looks like. So here's my core. The thicker this layer is on top of the ice cover, the less solar radiation can impinge and penetrate the ice cover. Solar radiation helps to weaken the ice, especially these long-grained crystal ice here. If this doesn't occur, your ice strength is maintained right into breakup. That can cause flooding through the ice jamming and the damming of ice pieces.
My research is trying to tackle one of the causes of premature breakup, which is the fluctuation of flow caused by hydropeaking operations. The Cotto Creek hydropower station is right upstream, and in wintertime they hydropeak a lot, and the ice cover is largely impacted by this operation. One of the products we're thinking of making is a risk map that could indicate the risk levels along the river channel to show how the ice cover responds to different scenarios of hydropeaking and different when the meteorological situation is different. One of the things we're hoping to incorporate in our modeling of the ice cover is to treat the dam release in the real form of waves instead of a moving volume of water. We're going to install a wave meter in the coming winter to monitor the volume of water moving downstream.
This research addresses the theme land, water management, and environmental change. We're looking at how nutrients and materials move into the riverine system, how those materials and nutrients are transformed within the river, and how also the sediment is being transported down the river and shaping the river with the hydraulic regime as well. All these have impacts on aquatic animal habitat and the river ice processes and on the water quality of the river.